gonna be a night exam. It's in this room. Okay. If you know that you have a conflict with any other exam, you need to go to the registrar office, and they will figure out which professor must give you the makeup. If I'm the instructor that should give you the makeup, just come to my office, and definitely I'm gonna arrange for a makeup. Yes. It's at 7 p.m. Now yes. It's about 1 hour, 10 minutes. If I'm you, I'll just kind of have it 1 hour, 20 minutes for me. In case you have another exam, plan that you'll be here 20 minutes until you go to the other place. Practice exam that I uploaded, as I told you, I uploaded 2 practice exams. I just want to bring your attention that this semester we're using a new book, and in the new book, which is the OWL book, we're covering more materials than what we used to do semester ago, which the practice exams are from. So when you read those practice exams, you're gonna see nothing about the limiting reagent or percentage yield, or all of these stuff that we're gonna talk about today. So keep in mind, if you don't see a question about a subject, that doesn't mean I don't ask about it. Probably I'm gonna ask about it, but it's a different book, so we're covering different material. The materials that's going to be on the exam is Chapter 1, Chapter 2, Chapter 3, and by then definitely we'll be covering Chapter 4. Okay? Usually I do review sessions the night before the exam. Till now, we didn't find kind of a room to reserve for that night. I'm going to let you know what we're going to do instead of the review session. If not a review session, I'll be in my office for 4 hours in addition to my regular office hours. I'll be in my office for additional 4 hours for anybody if you have any questions. But I'll update you about whether we have a review session or 4 hours in my office. So the last time we ended our talk about this problem, which is we have this following reaction. We wanted to determine the amount of H2SO4 consumed and the amount of moles, and I mean amount here, moles, of magnesium produced when 3.5 moles of magnesium nitride reacts. So your first step, whenever you get to this point, is to balance the equation. So let's balance the equation. And I think we did it the last time, but I'm going to go over it one more time. Plus ammonia to sulfate. I just want to bring your attention because I heard from some of you in the office hours. This 2 corresponds to the nitrogen, and yes, you have to multiply 2 times 4. You have here 8 hydrogen and 2 nitrogen. Now, when you have 4 here, it's only for the oxygen. It's only when you have the brackets for everything that the 2 is for the nitrogen and 2 times 4 for the hydrogen. Now, if you have, let's say here, AMG, this A, that means you have AMG, A sulfur, 4A oxygen. Okay? So note for this difference, guys, because I've heard from a good number of you that you're kind of confused about that one. Anyway, let's get started. I have 3 magnesium in here. So I'm going to put 3 magnesium in here. And as I said the last time, I wouldn't start with something that is in 2 places. I wouldn't begin balancing oxygen. I will keep oxygen to the last because it is in 2 products in the product side. Now nitrogen, I have 2 nitrogen here, 2 times N. Yes, I have 2 nitrogen. The nitrogen is balanced. 2H, I have 8H here, so I'm going to put a 4 times 2. Now I have 4 sulfates. 3 sulfates in the magnesium sulfate, 1 sulfur here, so the total is 4 sulfurs. So the sulfur is balanced here. 4 times 4, I have 16 oxygens. I have 3 times 4, 12, and I'm going to note it as oxygen so that you don't think it's 160 oxygen. and I have 4 oxygen, so the total of 16. Now the equation is balanced. Now the chemical reaction is balanced. I can go to the next step, which is determining how many moles of magnesium sulfate is produced or H2SO4 is consumed. So the first thing, as I said the last time, the equation, after balancing the equation, it's telling you something. It's telling you for each one, magnesium 3 and 2, you need 4 H2SO4. And you should take that into consideration when doing this calculation. And this is why we balance equation in the first place. So let's get started. You have 3. So the number of H2SO4 that's going to be consumed equal to 3.5 moles of the magnesium N2 multiply. I have for each 1 mole of magnesium, and I get this one from the stoichiometric coefficient. For each 1 mole of magnesium 3N2, I have 4 moles. I'm going to use 4 moles of H2SO4. And the 4, I get it from here, from the stoichiometric coefficient. Now, if you want, you can always use the dimensional analysis to guide you. So now, magnesium with magnesium. So I have the number of moles of hydrogen, so H2SO4, and that's 14 moles of H2SO4. So the number of moles of H2SO4 consumed in this process is 14 moles. Now the other question is how, and the amount of magnesium sulfate that is produced during the process. Again, I'm going to use the same process. I'm going to insert in here. So the number of moles of magnesium sulfate produced equal to, for each, I have 3.5 moles of Mg3N2. For each 1 mole, from the equation again, for each 1 mole of magnesium 3N2, I'm producing 3 moles of magnesium sulfate. So that's going to cancel that. I'm going to have about 10.5 moles of magnesium sulfate produced. Now, most of the time, they're going to ask you about the mass produced. This is what you're going to do when you have a procedure, an experimental procedure. We're going to give you number of moles, and you're going to find how much you produce. From the number of moles, definitely we learned how to go to the mass. Number of moles times molar mass, you can get the mass. And we're going to talk in a bit what is that, how to calculate the theoretical yield. Okay? So this is how we do that. Does that make sense? Make sense? So then you're ready for an eye clicker. Let's do an eye clicker. About the same
D. Opposite same. Yup. D.
Okay. I'm gonna give you 250 minutes to solve this. And this is NE in here. So the following is the reaction of calcium carbonate with hydrochloric acid. Calculate the mass, okay, the mass, not the moles, the mass in grams of CO2 produced when 2.48 mole of HCl are consumed. And this is the molar mass of CO2. Could you get the inside the box there is As usual, you can talk to each other, you can talk to the person behind you, in front of you, ask your friend. Okay. Okay, so I'm gonna stop it right here. And okay, I'll wait until everybody's sent. But send it fast. Okay, I'm gonna stop right here and check what was the most popular answer. And D is the most popular answer. And D is the right answer. Isn't that 56% of the class get it in 3 minutes? Okay, so our first step now, if you choose any A, B, C, either you forget to take stoichiometric coefficient into consideration. I did those calculations based on one of your mistakes. That not you. I mean, in general, the general mistakes for such a question. Either you didn't take stoichiometric coefficient into consideration, or you didn't. One of them is not stoichiometric coefficient into consideration. You didn't balance the equation in the first stage, or you used you put the stoichiometric coefficient instead 1/2, 2/1, or something like that. So let's see how we solve this. So the first thing is balancing the equation. So the balanced equation, this is the balanced equation. Always after I balance it, I double check. Calcium, 1 carbon, yes, I have 1 carbon. 3 oxygen, yes, 2 oxygen, 1, I'm good. 2H, I have 2H and 2Cl. Yes, it is balanced. Now my second step is we need the mass of CO2 produced. So either you can calculate first the number of moles, then multiply that by the molar mass, or do it in one-dimensional analysis. If I'm you, I'll do first the number of moles, then multiply it by the molar mass. It's up to you, you do whatever you feel you're confident to do. So the number of moles of CO2 produced equal for each first I have 2.48 moles of HCl. For each 2 moles of HCl, I produce 1 mole of CO2. So the number of moles for this one is 1.24 moles of CO2. Now I know that the number of moles equals the mass over the molar mass. Therefore, to get to the mass, I should multiply the number of moles of CO2 by the molar mass, which is 1.24 moles multiplied by the molar mass, 44 grams per mole, equal to 54.6 grams, which is D, the right answer. Okay? So this is if we have exactly how much of the reactant reacted, we can just calculate how much CO2, how much product we get. Okay? And I'll give you kind of 30 seconds to finish writing, because I feel that everybody is rushing there. Although the before and after, the slides as they are now, they're going to be online. So you can go home and open it and read what I just wrote there. Now, our next step, in this stage, in those 2 examples, we learned, okay, this is how much of HCl is consumed or of reactant consumed, how much product I have. Now, there is another question, which is the limiting reagent, or which is the limiting reactant? And before I go any further, I'm just going to give this example, and then we're going to go to the limiting reactant. Let's say I have a company, I'm a car company, and I have 8 car bodies, and the only thing that these cars are ready, all what they need is 4 tires, so that they are ready to be sold. So for each one car, we all know that I need 4 tires to get one car ready to be sold, ready for sale. Okay? Now, if I have 8 cars and 48 tires, okay, let's say I have 8 cars and 48 tires. For each car, I need 4 tires, right? I have 8 car bodies, and for each one car, which is the stoichiometry of this reaction, for each one car body, I need 4 tires. So I need 32 tires, right? And I have enough tires. But what's limiting me, I still have about 16 tires in excess, right? I have excess 16. So what's limiting me from producing more cars that are ready for sale is the body of the car, right? What's limiting you here from producing, instead of 8 cars ready for sale, for example, 9 or 10? Is it the tires or the body or the car bodies? Definitely the car bodies. And now, because this is the one that limiting us, we call it the limiting reactant. We can do the same calculation. We can say, but for the tires, we can say, okay, I have 48 tires. For each 4 tires, I need 1 car. How many cars I need to use all these tires? And we're gonna find that the number of cars that I need is much more than I have. And this tells me that the car body is the limiting reagent. Everybody understand this example? Okay, we're gonna do exactly the same. Cars and bodies, stoichiometric coefficient, but for reactants. And this is what I'm gonna do in the next step. So I have 12 more moles of butane is combined. So I have 12 moles of C4H10, and I'm combining them with 120 moles of oxygen. And the question is, what is the limiting reactant? What's gonna limit me from producing more CO2 and water? I'm gonna do exactly the same. The first step is to balance the equation, as we did in the cars and the car bodies and the tire. We said for each one tire, for each one body, this is how much tires I need. This is exactly the same. Here I already balanced the equation for sake of time. I balance it for you. So now I'm gonna calculate which is the limiting reagent. I'm gonna say, okay, the number of O2 that I need, I have 12 moles of C4H10. For each 2 moles of butane of C4H10, I need 13 moles of O2. Let's see if I have enough oxygen or not. So if we calculate the number of moles, I need 78 moles of oxygen. Right? So is oxygen the limiting reagent? Say yes or no, loud voice. No, it's not the limiting reagent. I have enough of oxygen. Let's see if we have enough of butane. Maybe we have now definitely the oxygen here is in excess, right? You can see that 78, 120. That by default tells you that this is the limiting reagent. Unless we have exactly, if I set 78 moles of oxygen, we may have just enough amount to do the reaction, and there is no limiting reagent. If I have in here given 78 moles of O2, I just have enough for the reaction to happen with nothing in excess. In here, oxygen is in excess, and C4H10 is the limiting reagent. Or reactant, it depends, sometimes we say this. Okay? So why? Now, we're doing all of this because the thing that let us know how many cars will be ready for sale is the limiting reagent, right? We based our calculation on the limiting reagent, not the excess. If I go one back, the ones that kind of determined how many cars are ready for sale is the limiting reagent, not the excess one. The excess, okay, I'm having excess of those. I don't have bodies, I'm not gonna do anything. And this is what we're gonna do in here. Most of the time, all the time, you're gonna have experimental procedure giving you number of moles, the same as I did here, 12 moles of butane, 120 of oxygen, and they're gonna ask you, what is the maximum yield, or the theoretical yield? So the theoretical yield, if theoretically your experiment went great, how much you gonna produce as a product? And that your first step is balance the chemical equation. Second step, determine the limiting reagent. And from the limiting reagent, calculate how much you're gonna produce. Let's say we're basing our calculation on CO2. So the question is, how much of CO2 you're gonna produce? You know now that C4H10 is your limiting reactant, so you're gonna say for the number of CO2 produced equal for 12 moles of C4H10, I have 12 moles. For each 2 moles of C4H10, I'm producing 8 moles of CO2. 8 moles. Can you see there? 8 moles of CO2. Now I'm gonna get the number of moles. I think I didn't calculate the number that is gonna be there, but 2, 4, so it's gonna be 4 times 12, 48 moles of CO2. So this is how much CO2 theoretically I'm gonna produce 48 moles of CO2. Now how to get the theoretical mass? You're gonna multiply by the molar mass of CO2. And this is how you're gonna calculate the theoretical mass for your experiments in a Gen Chem. When you go to the lab and they ask you what is your theoretical yield. So these are the steps. First, balance the equation, figure out the limiting reagent. From the limiting reagent, do the calculation how much. So the limiting reagent is the one that you're gonna use to calculate how much you produce. You wouldn't use the 120 oxygen, the excess, like the amount that is in excess. Okay? Get the idea? So ready for an eye clicker? Okay? And I'm gonna stop it at 2 minutes.
Those two.
I haven't done mine yet.
And the reaction is balanced for you there, just for the sake of time, to make it faster for you to handle it.
You that first kid. I was wanting to work.
That was the one that's haven't beneficial.
Is this the only other
You're gonna use the oxygen to calculate I'm just gonna change those numbers in here. Only those 2 numbers, okay? I apologize for that. So instead of 0.117, it's 0.100. Okay, another stop it at 3 minutes.
Two.
What?
6 eggs, 2.
Okay. The other two. Right?
Hmm?
The other two aren't.
Yeah. Oh,
It's obviously an H3. Do we even need to do a calculation to know that? You might be right though. Maybe she just didn't change the others because they're wrong.
So I'm gonna stop it right here and check what you think. So I have between A and C, 50-50 between A and C, and the right answer is C.
Ooh. How is it
So
safe?
let me go over that.
O2 wouldn't be the limiting
So,
reactant.
first of all, I have 2 grams of ammonia, 4 grams of oxygen. I have to change it to number of moles. You can either do it in one-dimensional analysis or in two-dimensional analysis or in 2 steps. So the first step is the number, the initial number. I'm going to say the initial number of ammonia equal to 2 grams over the molar mass of ammonia, which is 17.0 gram per mole, and that's going to end us up with 1.18 times 10 to the minus 1 mole of ammonia. Initial number of moles of oxygen, I have 4 grams over 32.0 gram per mole, and that's going to end us up with 1.25 times 10 to the minus 1 mole of oxygen. Now, our next step is to calculate how many oxygen and which is the limiting reagent. So I'm going to start. We're going to start with the following. So I'm going to say, okay, I have 1.118 times 10 to the minus 1 mole of NH3 for each 1 mole, for each 4 moles, because I have 4 NH3 plus 5 O2 giving me 4 NO plus 6 H2O. Okay? So for each 4 mole of NH3, I need 5 moles of oxygen. And if we do this calculation, 1.18 times 5 over 4, it's going to be 1.475 times 10 to the minus 1 moles of oxygen. Okay, let's see. Do I have enough oxygen? No. No or yes? No. So what is the limiting reagent? Oxygen. So I'm ended up with 2 choices, which is oxygen is the limiting reagent, which is C and D. Right? Now I have to calculate the number of moles of NO produced. So I'm going to say, okay, which is oxygen is the limiting reagent. So I'm going to use oxygen for my calculation. So I'm going to say, okay, I have 1.25 times 10 to the minus 1 mole of oxygen. So for each 5 moles of oxygen, of O2, I'm producing 4 moles of NO. So how much I have, and that's going to end up with 0.100 mole of NO. So this is how you do it. Definitely on OWL, there is much more about those. The more you practice, the faster you get. Definitely, OWL not going to give you the balanced equation. I did here just to get faster to home, because I can't give you 10 minutes to solve an I-click. And that's how we solve the limiting reagent. Okay? Now, if I ask you what is the theoretical yield of this reaction, what are you going to do? So I have the maximum number of moles that I can produce of NO, I'm going to multiply it by the molar mass of NO to get the mass. And that mass is the theoretical mass, the mass theoretical of NO. That's if everything went okay. If I started with 2 grams of ammonia and 4 grams of oxygen, if everything went okay, and there is no side reaction, nothing going on other than the reaction, this is 0.100 mole of NO is how much is the maximum yield. That's the maximum thing I'm going to get. We call it the maximum, the theoretical mass. Definitely you have to multiply it by the molar mass. Now, usually we do something called the percent yield. And the percent yield, it tells us how efficient was the reaction. And we calculate the percentage yield by the mass, the experimental mass, over the theoretical mass times 100. So, what is the experimental mass? Let's say you're doing the reaction, you ended up with, let's say, 2 grams of material. You weigh, on the weighing balance, you have 2 grams. That's the experimental yield. The experimental yield is the yield that you get at the end of your experiment. Now, the theoretical yield, let's say we're doing that reaction, which is ammonia plus oxygen, and you calculate the mass of nitrogen monoxide, although nitrogen monoxide is a gas, but let's say you calculated the mass, you figured out the mass of nitrogen monoxide experimentally over the mass theoretically is the one that we just calculated, which is 0.10 times the molar mass of NO, times 100. This is how we calculate the percentage yield of any experiment. I think you would do that in general. You would be asked to, in one of the experiments or 2 of them, to calculate the percentage yield. So the percentage yield is the mass experimental over the mass theoretical times 100. Okay? And the theoretical is you have to do, as I said, balance the equation, limiting reagent, calculate the maximum number of moles. From there, calculate the maximum mass that you can get. And by this, we're done from chapter 3. And we're going to get started with chapter 4, which has less calculation than chapter 3. Okay? So we have the chapter 4 going to talk about chemical reactions, and this is why I postponed those combustion reaction and the combustion reaction of hydrocarbons and metals till the end of chapter 3. So we have here metals and non-metals. Usually metals and non-metals, when they are combined with oxygen, when they burn with oxygen, they form the oxide form. And that's one of the reactions that you need to know. Whenever I say it's a reaction, I'm burning a metal with an oxygen, you need to know that, okay, that means she's asking me to put iron plus O2 to give the iron oxide or the oxide form. Now, how you're going to figure out this formula? Remember that you're going to go back to the idea of ionic compounds. If it is a metal, if it is a non-metal, it's a little bit harder. It depends on a lot of stuff. Also, non-metals react with oxygen to give sulfur. For example, sulfur is a non-metal. It's going to react with oxygen to give SO2. Phosphorus, it reacts with oxygen. It's also a non-metal. It will react with oxygen to form also an oxide. In other words, almost everything reacts with oxygen to form an oxide form. That's the bottom line of this. Now, the more interesting reaction is the reaction here. We talked about metals and non-metals. The more interesting one, the more interesting reaction is what we call the combustion reaction. And it is the reaction of hydrocarbons, which is something, hydrocarbon, that means something that is consisted of carbon and hydrogen. It must be carbon and hydrogen. It could be oxygen in addition. It could be carbon, hydrogen, oxygen and nitrogen. It could be carbon, hydrogen, nitrogen. But the main thing, a hydrocarbon, the name of hydrocarbon, it's something that contains carbon and hydrogen. And this hydrocarbons are one of the most important, and usually you have courses, you take courses about hydrocarbons, which are the organic compounds, which is Orgo 1 and Orgo 2, in case you are a pre-med in a pre-med kind of track. which is the combustion reaction of hydrocarbons. So I said for metals and non-metals, when we combine them or we burn them with oxygen, we get an oxide. For hydrocarbons, there is two reactions. There is a complete combustion reaction. So combustion is burning this hydrocarbon with oxygen. And there is an incomplete combustion reaction. I'm going to start with the complete combustion reaction, and I'm going to give an example. For example, methane, CH4, is a hydrocarbon. It's consisted of carbons and hydrogen. When I burn it with oxygen, it's going to give me CO2 plus water. Okay? And that's going to be gas. This is gas. This is gas. And this is, it depends on the temperature. It could be gas or heat. Okay? So this is what we call the complete combustion. So from now on, whenever I give you a hydrocarbon plus oxygen, it's going to give you CO2 and water under one condition. It's going to give you CO2 and water under one condition. I'm going to kind of tag this. Okay? Under one condition, if you have enough oxygen. Okay, what does that mean, I have enough oxygen? Let's say we're burning methane, we get some wood, and we begin burning it in this room, and I close all the doors of the room. What's going to happen to us soon after? We're going to get a carbon monoxide poisoning. Okay, and this is what happens when we do this reaction, exactly this reaction. In limited amount of oxygen, we're going to have carbon monoxide. Instead of carbon dioxide, we're going to have carbon monoxide. And this is, we call this incomplete combustion. And incomplete combustion happens when we don't have enough oxygen. Okay, this is what happens every semester. When I say incomplete oxygen, some students think, oh, so I can't balance the equation because I don't have enough oxygen. It's I don't have enough oxygen for carbon dioxide to be formed. It's not that I don't have enough oxygen to balance the equation. The equation gonna be balanced. And I find this every time in exams that students come back to my office saying, no, I write the right answer. We can't balance this equation because I don't have enough oxygen. No, it meant that you're doing the reaction in a closed place. It's not enough oxygen yet, it's going to be balanced. And this is why you have carbon monoxide, one oxygen instead of carbon dioxide. So in an incomplete combustion, you're going to form carbon monoxide when you burn hydrocarbons. But when you're doing this reaction outside, in the backyard, where we have a lot of oxygen, it's going to have enough to form CO2 instead of carbon monoxide. So complete combustion gonna give you CO2 plus water. Incomplete combustion gonna give you carbon monoxide and water. After that, now if I tell you what is the complete combustion of C6H10, you should be able to know that it's gonna definitely produce CO2 and water, and then you balance the equation. If I tell you what is the incomplete combustion of C10H8, you should know, oh, incomplete, that's going to give me carbon monoxide. It's the reaction of C10H8 plus oxygen to give me carbon monoxide plus water. Then you balance the equation. Get the idea? Okay. Now, both of them, definitely you have to balance it, and you can balance it as any other chemical reaction. Actually, we balance this at one of the slides. In one of these slides, we balance this. Now, what we're going to talk about in chapter 4. In chapter 4, all what we're going to talk about are, there are a lot of reactions out there. Some of them are organic, some of them are inorganic. That means that take place with carbon-hydrogen compounds, hydrocarbons, some with inorganic, some with metals, some with non-metals. But the one that we're going to talk about in this course is the reactions that take place in solution, in water. And we're going to only concentrate or focus on 4 reactions. Precipitation reaction, and this reaction is when I add A plus B, both of them are water soluble, and I end up with a precipitate. Let's say X, which is a precipitate. It's going to precipitate. That means I'm going to get two materials or 2 solutions that they are clear, they are homogeneous mixture, and I'm going to put them together, and suddenly I'm going to get a precipitate. We call these precipitate reactions. Acid-base reaction, it's as the name kind of sounds, it's an acid plus a base. Gas-forming reaction are the reaction that we're gonna add two stuff together to form a gas like CO2, H2S, SO2, so it's gonna form a gas. And lastly, the oxidation reduction reactions we're gonna talk about, which is it's gonna be losing and gaining electron or electron transfer reactions. Okay? Now, on each one of those, we're gonna spend at least 2 lectures on each part of this and each reaction. But before we get started, let me just make sure that we are all in the same boat regarding the definition of solvent and solute, electrolyte, non-electrolytes. So first, all of these reactions are gonna be in solution, and it's definitely we're gonna have a solvent and a solute. A solute is, let's say I have water plus salt. Salt is the solute, water is the solvent. And when I dissolve them together, I'm gonna have a homogeneous mixture because the salt dissolves in water. So these are the two definitions of solvent and solute if you don't know. Okay? Now, for solute, there is the classification of solute. There are two kinds of solutes that dissolves in water. It's either ionic or molecular. And ionic are the ionic compounds that we talked about and how we identify ionic compound and how we know from the periodic table that it is ionic. So, we have ionic or molecular which have covalent bonds. Okay? For ionic compounds, there are some stuff that totally dissolves in water, like NaCl. It totally dissolves in water. Definitely, the concentration play a role. If I put a lot of salt, we're gonna get to the saturation point and it wouldn't dissolve anymore. But mainly NaCl dissolves in water, totally dissolves in water. Now, there is some other element that, or ionic compound that partially dissolves in water, or don't dissolve in water at all. And this handout with the worksheet there is gonna guide you to know what are the solubility rules. And we're gonna spend about half a lecture how to read this and how to identify what is soluble and what is not soluble or insoluble in water. This is a worksheet just so that you get used how to use this table. You may say, oh, I definitely know how to use the table. I had cases, students don't know how to use this table, although it's going to be given to you in the exam. I'm going to post the key for this worksheet sometimes on Friday, and we're going to talk about more about the ionic compound solubility using those solubility rules. And some of these ionic compounds are not non-soluble at all in water. Now, for molecular compounds, some are soluble, some totally soluble, some partially, some insoluble at all in water. Now, definitely all of you know that from your everyday experience that water is a universal solvent for us as human beings because it dissolves almost everything except the oil and the fat after the hamburger. Water doesn't dissolve it unless we use some salt. So the water works as a universal solvent because of its polarity, because it is polar, because the hydrogen here, it have a partial positive charge, the hydrogen partial positive, and the oxygen have a partial negative. And we're going to talk more about polarity and how we figure polarity and which compounds are polar and non-polar in chapter 6 later on. So let's say I have NaCl, I'm adding it to the water. What's going to happen that the Na plus going to be solvated by the kind of the partial mine is going to be around, more than one oxygen around the Na, and for the Cl mine is going to be those partially positive, it's not totally positive, partially positive H around the Cl, and this is how things are solvated in water. That's if they are ionic. If they are covalent, it most probably it's hydrogen bonding or hydrophilic interaction. But for the moment, you have to think about it that water is dissolving this stuff because it's polar, it has this partial plus, partial minus that solvate the stuff. Now, let's say I have NaCl in water, and then definitely the NaCl is dissolved in water. If I apply voltage inside this solution, what's going to happen? Let's say this is the minus and this is the plus charge voltage. What's going to happen? That the Na plus is going to go to the minus electrode, and the Cl minus is going to go to the plus, and the electron going to pass in that beaker, and it's going to conduct electricity, and that solution going to conduct electricity. And we call the compounds or the ionic compound that dissolves in water and conduct electricity, or any other thing that dissolves in water and conduct electricity, we call them electrolytes. That means they conduct electricity. And those that we dissolve them in water and they don't conduct electricity, we call them non-electrolytes. And this is the definition of electrolyte and non-electrolyte. I think we have enough time, so Jay gonna show us a quick demo here of things that dissolves in water and whether they're gonna conduct electricity or not. Okay. So, what we have in here is, so first let's do something. Okay. So, I'm gonna kind of try to dim the light in here so that, okay guys, we're not done yet, okay? You can't leave. So, what we have here is an ACl. And as you can see, what I did, we have a high voltage in here that is connected in series to those lamps. And what I'll do is I have an ACl in here, and I'm dipping this electrode in there. And yes, it is a good electrolyte. And all of these lights. Now let's try the vinegar or the salt. Is this it? Okay. Okay. Vinegar. Let's try vinegar, which is the acetic acid that you have in. It's the vinegar. It's called acetic acid. What is your expectation? What do you think? We didn't discuss it yet, but what is your expectation? How many of those gonna be turned on? 1, 2, none? 2, okay. Close enough. 3. And on Wednesday we're gonna learn why 3. Why acetic acid would do just the 3 lamps. Let's try the HCl, which is also an acid. Let's try HCl. Okay, what do you think? It's an acid, it's the same as acetic acid. Would it conduct electricity the same way? What do you think? I'm hearing no. How many? 1, 2, 3, 4. So keep it in mind. HCl makes the 5 lamps goes on. Acetic acid only 3. Now, what do you think about what you drink every day? What do you think? Yes? No? Yes? Okay, let's see. How many lamps do you think?
What is it actually? I don't know.
5? Okay,
Gatorade, yeah.
let's see. Okay, definitely if you read the nutrition facts there, it has electrolytes. They kind of write it as sodium, as if it is a metal. Definitely it's not a metal there. It's an A+, it's ions, but they tend to say sodium, potassium. We know that if we put sodium in water, it's going to make an explosion. But they seem to write it as sodium, potassium, but you should know that this is an A+, K+, and this is why it conducts electricity. Even the energy drink that you drink. Let's try sugar, and then I'll leave you to go. We have water and sugar. What do you think? Sugar is a hydrocarbon and it dissolves in water. What do you think? No? You're right. No, sugar is not. So keep what you saw today so that we discuss it on Wednesday. Keep it in mind.